In this lesson, we're going to talk about graphing the set of all possible solutions. And if you want to read through these, you can. We've talked a lot about systems of equations, so that's two equations and two unknowns, and therefore their answer or solution can be represented as ordered pairs because they are there is an x and a y. When we plot our ordered pairs, if we're just graphing a line or any other curve, if we plot those ordered pairs, it's going to create a line if it's a linear equation, but if it's not a linear equation, then it might it will create a non-line, which would have some sort of curvature to it. If we're looking at an equation of a line, possibly or a quadratic or an exponential equation, in that case, the solution set's going to be infinite. It will be all ordered pairs along that line or along that curve that will be answers to our problem or to our equation. So for this one, this is very straightforward, but if I solve for y so that I put it in slope-intercept form, then I have a y-intercept of -2 and a slope of -3. So we all know how to graph a line, I hope, but the biggest thing is noticing that any set of ordered pairs that falls on this line will satisfy this equation, and that because we have arrows going in each direction, that means it extends infinitely in each direction, and therefore we would have an infinite number of solutions that would fall on that line. For this one, you should recognize that the variable is the exponent, and therefore it's an exponential equation. For this one, we're going to create a t-chart, and I'm going to select some values to plug in. I'm going to plug in -2, -1, 0, 1, and 2 for now. And when I plug those in, remember I'm plugging them in as an exponent, so 3 to the -2. You could do this in your calculator, but remember that that is 1 over 3 squared, so that becomes 1/9. If I plug in -1, I get 1 over 3. If I plug in 0, remember anything to the 0 power is 1. If I plug in 1, I get 3. If I plug in 3, I get 9. So let's plot those points. I get -2 and 1/9, which is really hard to show, but -1 and 1/3, 0 and 1, 1 and 3, 2 and 9, and then if I were to plug in 3, I would get 27, which would be further than what I have on my graph. Connecting those points, I end up with this curve, and remember that is my sort of one of my basics for an exponential graph. If you recall, our graph of an exponential will approach 0 as a y value, but will never actually reach 0, because the larger the negative number gets, then basically just the larger my denominator gets. So I just end up with 1 over a very large number, which would just be very, very, very small, but never equivalent to 0. Alright, here is our word problem. The Russell family is driving 1,000 miles to the beach for vacation. They are driving at an average rate of 60 miles per hour. Write an equation that represents the distance remaining in miles and the time in hours that they have been driving until they reach the beach. They plan on stopping 4 times during the trip. Draw a graph that represents all of the possible distances and times that they could stop on their drive. So first we're going to go ahead and write our equation. So we're looking at 1,000 minus 60 times x. In this case, they have 1,000 miles to go, and since we're looking at the distance remaining, it's 1,000 minus however much they've gone, and however far they've gone is 60 times x, and x being the number of hours. So that's our equation, and we're going to go ahead and graph this here. So I'm going to write our equation up here. We said it was 1,000 minus 60x. So if you look here, we're counting by 20s. So this top right here would be 1,000. And I'm going to go down a slope of negative 60. So I'm going to go down 20, 40, 60, and over 1. 20, 40, 60, and over 1. And I could continue that all the way down. Now, if you recall, the second part of our problem was asking us, it was talking about them making rest or making stops along the way, and it asked us to identify all of the possible, or to show, represent all of the possible stops or places to stop. So it says right here they plan on stopping 4 times. Draw a graph that represents all of the possible distances and times that they could stop on their drive. So basically we're just representing our equation, because technically they could stop anywhere along here, because that would be where the equation would be graphed. However, realistically, we know that if you're planning on stopping at a rest area, whether that's a fast food place or an actual rest area, they don't occur everywhere. It would only be certain spots along the way. But this is how we would just go ahead and represent all of the technical possibilities along this route.